All right, the acceleration due to gravity on the surface of a planet is 3 times as large as it is on the surface of Earth. The mass density of the planet is known to be twice that of the Earth. What is the radius of this planet in terms of Earth radius? Okay, so let's say this is the Earth, this is the planet. Okay, so mass, okay, this is the force with which Earth pulls you down, and that's the force with which the planet pulls you down. And all right, so again, your mass cancels. What they tell you is the acceleration due to gravity on the surface of a planet is 3 times larger. The acceleration due to gravity on the surface is, this thing is 3 times larger than that. So G planet over G Earth equal to G okay, again that cancels, and they tell you that this, oops, they tell you that this is 3, this is 3, so 3 equal to they also tell you the mass density of the planet is known to be twice that of Earth. All right, so what they also tell you is mass of the planet divided by 4 pi by 3. Okay, this is the mass of the planet divided by its volume. That is twice that of Earth. Okay. So you see from this thing, again, that cancels, that cancels. What I'm going to do is, I'm going to take one of the radii and bring it over there, and bring that over here. So let's make sure we understand this. Okay, tell you what, I'll bring this to the other page. Okay, so MP over RP square divided by ME over RE square equal to 2 RP over RE. Did you guys see what I did? So ME over RE square, I took that. All right, this is the same thing as MP over RP square divided by RP equal to 2 times ME over RE square over RE. Everybody see that? All right, and now I'll bring this down there, this over there. So this divided by this is 2 times that. All right, why did we do that? Because this guy is what we have here. Okay. So 3 is equal to that. So this is equal to 3. So 3 equal to 2 RP Okay, so what are we saying? The radius of the planet is 1.5 times the radius of the Earth. So the radius of the Earth is 6,400 kilometers. This radius of this planet is 9,600 kilometers. Okay. And do you guys have any questions on that? Yes? Go ahead. Lost where? This step?
Yeah, or how you went from the previous one.
Okay, so,
Like that to the next one.
okay. From here to here? No, this is one independent thing. So, and then this is a second thing that they gave us. They say the mass density of the planet is known to be twice that of Earth. Mass density is mass divided by volume. So this is the density of planet is two times the density of Earth. Yeah. Any other questions on that? Okay, this problem says, what is the escape speed of a satellite located at the moon's orbit around Earth? Assume the moon is not nearby. So, all right. So we'll have to look up Earth-Moon distance. Okay. They want you to find the escape velocity from there. So let's say that that object is hovering over there and it wants to fire its rockets and escape the Earth's grip. Okay, so what you want is, if you have escape velocity, if you escape, what will happen at infinity? You go to infinity and you come to rest. Okay, so what you want is, here's how you calculate the escape velocity. The kinetic energy at this point plus the potential energy at that point should equal 0. Because once you go to infinity, you need to come to rest. So your total energy should be 0. Okay? So that's what it works out to. And and this is how they derive the escape velocity formula. So the escape, and this is the escape velocity. Okay, so what is this saying? The escape velocity from Earth when you start off at that distance, Earth-Moon distance. Do you guys remember what is the escape velocity from the surface of the Earth?
11 kilometers.
Very good, 11.2 kilometers. Okay, so if you try and escape from higher and higher, if this increases, the escape velocity decreases. Okay? All right, so now let's put in the numbers. Mass of the Earth is 6 times 10 to the 24 kgs. And Earth-Moon distance, so we'll have to look that up. Okay, so 3.84 into 5, 10 to the power 8 meters. Okay. All right, so again, let's take care of powers of 10. This is 24 minus 11 is 13, and 13 minus 8 is 5. So what we'll do is we'll spend one of that here. So, and, or, okay, 24, 13, 5. We'll borrow 1 and 6. Okay, so into 10 to the 3 meters per second, 2 into 6.67 into 0.6 divided by 3.84. Okay, so that's what it works out to. So the escape velocity from there is 1.44 kilometers per second. Okay. So let me ask you this. The moon's orbital velocity, can you say anything about the moon's orbital velocity now that you know this number? Very good. So the moon is not escaping, the moon is bound to Earth. So the moon's orbital velocity is less than that. Okay? So let's look up moon's orbital velocity. 1.02 kilometers per second. Yep. The escape velocity from the surface of the Earth was 11 kilometers a second, and the space shuttle went around at 8 kilometers a second. Okay? Any questions on that one? Okay. An average-sized asteroid located 5 times 10 to the 7 kilometers from the Earth with a mass of 2 times 10 to the 13 kg is detected headed directly toward Earth with a speed of 2 kilometers per second. What will its speed be just before it hits our atmosphere? You may ignore the size of the asteroid. Okay. So okay, so it's going at 2 kilometers a second. Now, this is an energy conservation problem. Energy is conserved. Okay. So kinetic energy plus potential energy is equal to the final kinetic energy plus potential energy. And here's how you calculate so this is the correct formula for the potential energy. Okay. And that's the mass of the Earth. Our final is just the radius of the Earth. So it's essentially hit the surface of the Earth. This will be the radius of the Earth. Notice the mass of the asteroid cancels, meaning no matter which what asteroid it is that starts it all. They all hit at the same speed, assuming they start at the same speed. Okay. All right. So V final square is what we want to find. V final square is V initial square plus GME R final minus GME R initial. Okay, so this is 2 kilometers square, which is 2,000, 2 into 10 to the power 3 square plus G is 6.67 into 10 minus 11, and I'm not going to write units, 24. Our final is the radius of the Earth, and the radius of the Earth is 6.4 times 10 to the 6 meters, minus our initial was 50 times 10 to the 6 meters. Okay. So let's take, that's 10 to the minus 11, that's 10 to the power 13, and then, so 10 to the power 7 is what is left. So, okay. I'm going to go to a new page. Vf square is V initial square, which is 4 times 10 to the 6 plus 6.67 into 10 to the 7 Okay, so that's what I get. I hope I didn't make any mistakes. Yes. Oh, never mind. That's kilometers, not meters. So that's 50 times 10 to the 9. Still doesn't change much. 24. This speed is bothering me. It should be a little higher. Okay, that's 13 and 6, 7, and that should be 10 to the 3. And essentially this is 0. You can throw this away. So so this becomes 62.5. Okay, 8.16. All right. Is there any place you guys can check the answer? All right. What will the kinetic energy of the asteroid in the previous problem just before it hits the Earth? Okay. So, one of the theories is the dinosaurs got killed by a large asteroid hitting the Earth, and all that dirt splashing and blocking away the sun for 2-3 years and stuff like that for many years. All right, so we'll let this hit the Earth, see how much energy it deposits, okay, and compare that to atom bombs. So the kinetic energy would be of the asteroid would be 1/2 mv squared, and the mass of the asteroid is 2 into 10 to the 13 kgs. Just the Earth, mass of the Earth is 10 to the 24 kgs, so you need almost 1 trillion of those to make the Earth. Okay, so again, compared to the Earth, it's a small rock. Okay, so that's 10 to the 6, 10 to the 19. That cancels. So this is an interesting number. This is how much energy we use on the Earth per year. Okay, so that's how much the asteroid's energy would be. Okay, compare this output to a large fission bomb of 21,000 terajoules. So kinetic energy divided by bomb energy. And terajoules is 10 to the 15 joules. A terajoule is a trillion joules. So it's 10 to the 12. So that's 10 to the 15. So 300,000 of those bombs. Okay. That would cause a bit of damage. Yep. You guys understand? I guess that would be good enough to wipe out the dinosaurs. Are you guys understanding this? You guys need a break? Are you guys good to go? Yeah, right. So, astronomical observations of our Milky Way galaxy indicate that a mass of about 8 times 10 to the solar masses indicate that it has a mass of about that much solar masses. 800 billion solar masses. A star orbiting on the galaxy's periphery is about 6 times 10 to the 4 light years from its center. What should the orbital period of this star be? So this is going to show you the evidence for dark matter, okay? This problem. If the period is 6 times 10 to the 7 years instead, what is the mass of the galaxy? Such calculations are used to imply the existence of other matter such as very massive black holes at the center of the Milky Way galaxy. Well, and dark matter as well, okay. So here's the galaxy. Now here's a star going around at the periphery. Okay, so this guy is affected by all the mass inside his orbit. And you can treat all this mass as a point object. Okay, so the idea is, okay, you count up all the stars, which is that many stars. You know the mass of the sun, so it's that equivalent to that many suns. So you know you can see that much mass. And then you calculate the orbital velocity. That's how you can calculate how fast this should be going. Okay? And if this guy is going faster than that, that must mean that there's more mass in here. If he's going slower, then you overestimated the mass. All right. Now for this, we'll use Kepler's third law. Kepler's third law says the orbital period square divided by the radius cube equal to 4 pi square g mass enclosed. And let me make sure I got the factors correct. Yeah, some period square. Okay. Okay, so what this formula, Kepler's third law, is saying is anything orbiting its period square divided by its radius cubed is equal to 4 pi squared g times the mass inside. Okay? So the mass, this mass is 4 pi squared g r cubed by t squared. Okay, a star orbiting is about, what should the orbital period of the star be? Okay, we'll calculate the orbital period. That's what we want to calculate. The mass inside is 8 times 10 to the 11 solar masses. Here's the symbol for the solar mass. This is the mass of our sun. And so the mass of the galaxy is 800 billion solar masses. Okay, now we're ready to put in the numbers. R is, this is given in light years, 10 to the 4 light years. And we have to convert it into meters. Okay, so that's light years, and this is cubed. So you got to cube this and that. And then G times 800 billion. And the mass of the sun is 10 to the 30 kgs. Okay, so when you're doing calculations like this, you're dealing with a lot of large numbers. And like I said again, you want to take care of the powers of 10 in your head. All right, so watch this. That's 15 and 4 is 19. 19 times 3 is 57. And 57 minus 30 is 27. 27 minus 9 is 18. 18, and then we'll spend 2 more, so 16. Square root of that is 8. And this is time, so that comes out in seconds. Okay. Oops. I didn't write down G. So scratch that. Okay, let's do this again. 1957, 68, 68 minus 39 is 29. Okay. $29, and we'll, so 4 pi squared into 6 cubed into 9.46 cubed into 10. Ha, I messed up, didn't I? Okay, you guys do it in your head, I'll do it in my head. 1957, 68, 66, 36, and 27, 26. All right, and then all right, that's what I get.
29?
Huh?
Is it 29? The power, the order of magnitude?
And then you have to take a square root.
Oh, okay.
Mhm.
Where does the 9.46 times 10 to the 15th come from? Is that a conversion of light years?
Yeah, meters to light years.
Oh, okay.
How did you get from 29 to 13?
Oh, well, actually, I spent 27, and then I took one of those, left one of those tens there, 26 to 13. Square root of 26. So the period, I got 284 million years. What should be the orbital period of the star? I got that much, 284 million years. Instead, the period is 60 million years. Okay, If the period is much smaller, the mass is much greater. Did you guys understand that? And so that's the kind of stuff that's evidence for dark matter. Okay, so basically it's the following. The more massive an object, the faster you have to go. Okay, the speed of something is easy to measure. Okay, so this is what you do in astronomy. You measure the speed of stuff, and then you know the mass of this guy, and you look at it, and shoot, he's not as heavy. You don't see as much mass. All right, that's what this graph was showing you. So this has been a puzzle. This has been bothering people since the 1930s and 40s and stuff like that. Mm. Where the heck is that graph?
Can I ask a quick question on that last problem I just did?
Mm-hmm.
You were saying that if the
Mm.
orbital period is smaller, it would have to account for a larger gravitational constant, correct? Or was it
No,
mass?
mass.
Mass.
Mm-hmm.
Mass. Thank you.
So here, this graph, so here's the orbital period. The orbital period is not falling off, okay? So what this is showing you is, okay, see this is all the mass you're seeing.
Mm-hmm.
Okay, so if there was no more mass, if you start increasing the radius, so, okay, where's the problem? Okay, so if you see no more mass,
Mm-hmm.
if you increase the radius, the orbital period should fall off. You see, the orbital period is, this is orbital velocity. Okay, here's velocity. So mv squared, this is the centripetal acceleration, gmm by r. Okay, so if the mass remains constant, this mass cancels. Okay. Okay, so what this is showing you is, what this graph is showing you is, so now you're not seeing any more stars. This mass is constant. So as you go further out, r increases, the velocity should decrease. And it is not. So there must be some unseen mass over there. Since this velocity is not decreasing, this mass keeps increasing, meaning there's some mass out there that you can't see.
How do you measure the velocity of something you can't see?
Oh no, these are velocities of stars that you can see. These are stars. Single stars, you can measure the velocity of those. Okay. All right, so we calculated the orbital period is 284 million years. By the way, our sun is somewhere there, and our sun goes around the galaxy in 200 million years. Okay. So if its period is 6 times that, instead, what is the mass of the galaxy? Okay. So I'm going to put this formula back. T square so mass is okay, so what the calculated period is 284 million years. And the actual period is 60 million years. Okay, so calculated mass divided by actual mass, or we'll do actual mass divided by calculated mass should equal 4 pi. G. R is the same, actual square over okay, all this stuff cancels. Okay, so here was the calculated mass, calculated period. And so So there's roughly 22 times more mass than you can see. Okay. Okay. So again, you've seen many talks. Okay. Here's the idea. The radius, this is easy to measure. Okay. And this velocity is easy to measure. Okay. So from the velocity, you can calculate the period. Okay. So once you know how fast something is going and how far it is, you can calculate this thing. This then can be calculated. So T square over R cube is 4. This is Kepler's third law. This central mass, this is the central mass. So that's what you want to know the mass of this central object, find a star that's going around, measure its speed and radius, and then you can calculate this mass. And if you don't see that mass, then there's something wrong. Okay? Okay. Okay, I'll do one more problem. We'll do this one and that will end there. So what would be the Schwarzschild radius in light years if our Milky Way galaxy of 100 billion stars collapsed into a black hole. So we have 100 billion solar masses. If we turned it into a black hole, how big would this black hole be? Okay, so you guys know the size of our galaxy. It's about 100,000 light years. Okay, and its mass is 100 billion solar masses. Okay. Compare this to our distance from the center, which is about 13,000. So what this is saying is our sun is somewhere here. That's 13,000 light years. Okay. Okay. But we are going to take all these stars and collapse it into a black hole. Okay. The radius of the Schwarzschild radius is given by 2g I just want to make sure I don't want to get Okay, so there's the Schwarzschild radius. All right, so what this formula is saying is if you want to turn this mass into a black hole, you got to squeeze it within this radius. Okay, at that radius, the escape velocity is the speed of light. So that's where that formula comes from. Okay. Okay, so let's calculate the Schwarzschild radius. 2g is 6.67 into 10 minus 11. The mass is 100 billion solar masses. And that's the mass of our sun. Divided by c squared. 3 into 10 to the 8 squared. And again, I haven't put down units because it will get messy otherwise. Okay, I'm going to take care of powers of 10. 30, 39, 41, 30, 4, that's 16, 14, 7. $39, 41, 30, 14, 7. Okay.
Oh, at the end, is that 10 to the 3 or 10 to the 30?
10 to the 30. That's the solar mass. Sorry. You want me? I'll make more room. Okay, so, and then this is 2 times 6.67 into 2 divided by 9. All right, so this is the radius is 17 million meters. Whoa, what went wrong? Mm. There's no square root. Okay. And so this is, and we'll convert this to light years. 2.946 into 10. .42 light days or 0.031 light year. What that means, okay, so again, so here the radius of the sun's orbit. If you turn this entire thing into a black hole, it would be almost a point on this diagram. Okay, what this tells you is it takes light, so you turn the entire Milky Way into a black hole. It would take light 11.4 days to get from the center to there. That's how small the black hole would be. How long does it take light to get from the sun to the earth? 8 minutes. Okay, so that's 8 light minutes. This would be 11 light days. Okay, that's what that means.